Thank you, Meghna. Hi, everyone. My name is Tomer. I'm a graduate student from Technion in Israel. Thank you very much for joining us. It's really nice to see everybody tuning in to the WDSA's Graduate Student Test Committee's second webinar. This is the second of a series of webinars that we plan to hold. This webinar is going to be about applications of artificial intelligence technology in water distribution systems. And we have the great pleasure to have with us three highly regarded speakers today. Dr. Zoran Kapelan from TU Delft in the Netherlands, Dr. Stefano Galelli from Cornell University, and Dr. Demetrios Eliades from KIOS Research Institute in the University of Cyprus. Before we begin, I would just like to acknowledge my friends that helped make this webinar possible: Meghna Thomas from UT Austin, and Camilo Salcedo from the University of Arizona, Ali Salem from the University of Illinois, and Dr. Sabrina Joad from the University of British Columbia. We also plan to hold a couple of activities during EWRI, so for anybody who's planning on attending, stay tuned. And I think we can now begin. We'll begin with Dr. Zoran Kapelan. Please, thank you for being here, and the floor is yours.
Thank you, Tomer. Thank you. I'm really happy to be here. Let me just share my presentation first. Hopefully you can see the presentation now in presentation mode. So the title of my talk today is Artificial Intelligence for Smarter Urban Water Infrastructure. And I work as a professor of these systems at Delft University of Technology in the Netherlands. A bit of warning to some of you. I've seen some people on the list. Some of you may have seen some of these slides before. More than once, like Miriam Blocker, for example. But yes, the main purpose, if I understood correctly today, is to do this seminar for the students and the researchers to demonstrate the benefits of AI and so on. So my research focus is really on urban water infrastructure, covering the full water cycle, anything to do either with drinking water, distribution, or the urban drainage, stormwater, wastewater collection and disposal. When I say different issues, it's really, all sorts of different aspects of both system operation and planning or maintaining and adapting these systems to climate change in terms of operation, both normal operating conditions and failing conditions, and both to do with water quantity and quality aspects, including real time. Now, these infrastructure systems are facing many challenges, and I'm not going to spend too much time on this. I'm sure you're aware of the list that I'm showing here. This is true for water distribution systems, which are the focus of talk today, but also for urban drainage systems. So why then use AI? Well, AI can actually help us make the system smarter and address some of these challenges that we are facing. How can AI help? It can help us better understand the network performance or state. A lot of methods have been developed for predicting system state and so on. It can help us better utilize all sorts of resources, not just water, but also energy, treatment chemicals, and the rest under normal operating conditions. And it can also help us when things fail, either small failures like pipe bursts or some more catastrophic failures. It can help us detect or maybe even predict these events before they take place. So it basically enables us to be more proactive, to improve the management of assets of these systems, which are normally high in value, and ultimately improve the service that we all receive at home. The figure here is from the Smart Water Networks Forum. I quite like it, that's why I'm showing it here. It's a layered version of a urban water system, or in this case, water distribution system. It starts with a physical layer, that's your pipes, pumps, tanks, and so on. At some point back in the 1980s, SCADA systems were introduced, so we started sensing and some sort of, simple control, mainly and treatment works. But later on, this expanded into collection and communication additional data with increased number of sensors in the field. And once this was done, and this was typically done in the early 2000s, in some companies this is happening only now, a lot of data was collected, and this data was mainly this came up with a nice software, with a nice visualization software from different software vendors, who enabled you to, the control room operators, to look at this software, but not much more beyond that. The real value of AI is in this fifth layer, which is the data fusion and analysis layer. And this is where we basically use this raw data coming from sensors and elsewhere in the system and try and extract useful information. And if we do this successfully, then AI can be really helpful. In terms of AI applications, they can be far and wide. I'm listing here only the applications I've been working on personally since the 90s. Yes, at the top of the list is the detection of pipe bursts and leaks and equipment failures in both distribution systems and treatment plants, but also the equivalent blockages in urban drainage systems. State estimation is an obvious one, where you're trying to predict pressures and flows, or flows and levels in drainage systems. System load forecasting, you can use these AI systems to predict water consumption or rainfall. You can use them for asset pipe condition assessment. The figure here shows one of those AI systems which I've been developing over a number of years. This is currently being commercialized. It's using computer vision and the form of deep learning to try and detect, displaced joints and all sorts of other defects in this case, urban drainage pipes. Water quality can be predicted. You can have systems for discoloration, early warning. Of course, operational optimization like pump scheduling. Distribution system optimization in general, this is optimizing long-term, the configuration of the system and adapting them to climate change and other uncertainties. It can also be used for sensor data validation, placement. Lately, I've been using AI even for sediment transport prediction in sewers to try and predict the exact flow conditions and at which the sediment in sewer system starts moving. And of course, many other, one of the recent applications is the detection of plastics, for example, in urban water canals and rivers in the Netherlands and so on. What are the methods I have been using over the years? With quite a few different methods, but as in most cases, and probably as in cases with most of you, the center of the scene is the artificial neural networks. And initially, we used more conventional feed-forward neural networks. I think I tried my first one for the purpose of pump scheduling, for model emulation for pump scheduling back in 1996. But neural networks have evolved a lot since then. And you have all these advanced deep learning networks, LSTM, long short-term memory, convolutional neural networks, and lately graph neural networks, which grew in complexity and so on, but which also now provide new opportunities, new level of learning to solve all sorts of problems in water engineering. I've been combining this, especially recently, with computer vision as well. In addition to neural networks, I've been quite fond of random forests, which are based on decision trees. They've proved to be useful on a number of occasions, and when compared to other methods, typically do very well. And of course, many other methods. I'm sure you're all aware of gradient boosting and extreme boosting methods and all sorts of other things. I'm not going to go through the full list. The figure here is showing some of the more recent work, collaboration with colleagues in China. In this case, we are using deep learning combined with computer vision to detect, to estimate more precisely the rainfall intensity from a CCTV image of rain. These are standard CCTV images you can find on CCTV cameras in cities. So rather than measuring at locations where there are no measurements, we try and estimate the rainfall intensity.
Recording in progress.
Let me show you, time is limited, of course, and I'll focus only on one example to show you how AI can be used in distribution systems, in this particular case for the detection of pipe bursts and associated leaks, but also other events like equipment failure. And that's exactly the challenge here. You have a water distribution network. In this case, this is the network from the UK, so it was sectorized into DMAs. It doesn't have to be, but in this particular case, each DMA has has a flow meter at the inlet point, and it has a pressure measurement at the critical node and maybe additional pressure measurements at the inlet node. And even though the network can be, several hundred pipes large, it doesn't have more than 2 or 3 sensors, or at least it didn't used to have when this was developed about 10 to 15 years ago. The data that is used for this detection are pressure and flow measurements, typically coming in every 15 minutes. And I just want to stress that this is data analytics type technology. There is no Ethernet involved here or any other hydraulic or any other simulation model. All the predictions and any detections, everything is done by the AI methods. And this methodology enables a more proactive approach, which I will show you in a minute how and why. How does it work? It works in different stages. In the first stage, in phase 1, you use the AI-based signal prediction. So artificial neural network in this case is used to predict the value of pressure signals or flow signals at each of the sensors in the network for the forthcoming short period, say 15 minutes to 1 hour, depending on the application. What the figure shows here is 2 such signals, flow and pressure. The blue line are the measurements, the green line are the predictions of the neural network on the trained part, of the calibration part, and the red line is the prediction of the neural network on the unseen data. And as you can see, the red line is quite well matching the observations, which is critical for this thing. So this is prediction of the pressures and flows in the system, assuming no events in a distribution system, assuming no pipe bursts, equipment failures, anything like that, okay? Then you use these predictions to compare with observations. So at some point, you predict for the next 15 minutes, observation comes in. This can be both for flow or pressure. You predict, observation comes in. And as long as the 2 stay close to each other, you can kind of conclude there is nothing unusual going on in the system. However, if at some point there is a deviation between the 2, this brings you some form of evidence that something is going on in the system. Now, this particular type of evidence is really good for instantaneous events, for medium to larger bursts and so on. Other forms of evidence can be collected. This is just another example. For each of these sensors in the system, given the recurring nature of water consumption, which is pretty much similar day to day, what you can do is you can work out for each hour of the day or for each 15-minute interval of the day, you can work out the confidence intervals. Arrange an interval in which you normally expect the pressure or flow to be at that given sensor at that location. And then, obviously, if you get an observed value outside of these bounds, that's another form of evidence that something is going on in the system. Other forms of evidence can be collected as well. And once you collect a number of these, and this is where you apply your engineering knowledge, by the way, then you can put this into something like a Bayesian network. So this is a network which at the top is fed by these different forms of evidence, typically at the pre-pastime interval or the several pastime intervals. And then the network works out its magic after it's being trained, and it predicts the probability that this particular system is experiencing some sort of failure event, either a burst or equipment failure or something else. And if you then put a threshold value on this probability, say probability is, 70% or more, then you can raise an alarm. And that's how it pretty much works in a nutshell. So it's a combination of AI, but also engineering knowledge that is used to develop it. Let me show you examples how this works. So this is an example of a large burst. This is a DMA where it was a very large burst, so the flow rate increased a lot and the pressure dropped a lot. So it was not difficult for the method to basically raise an alarm. As you can see, alarm was raised as soon as the pressure dropped or flow increased, only within 15 or 30 minutes. By the way, the blue line is the actual signal, either pressure or flow. The yellow lines is that probability that Bayesian network is outputting for that particular location. And it's calculated again every 15 minutes, but it's shown here in the graph only after the alarm to make the graph simpler. So you could argue, in a case of a large burst like this, do you really need a sophisticated AI-based system to detect a burst? Because the water will probably appear on the surface. Well, yes and no. If this burst happens, like in this case, 45 minutes after midnight, then it's actually useful to predict it because company then becomes aware of it immediately. They don't have to wait until the next morning for someone to report it. In theory, if they are well organized, they could actually go out and fix this burst before the people wake up. Now, where the method works really well and why it is so useful is on the medium to smaller burst. And this is the other extreme. This is an example of a very small burst. In this case, burst flow rate increased only by 2%. The burst flow rate was only 2% of the average inflow into this DMA in the network. And of course, this is not visible by a naked eye. And yes, of course, the system can't pick up all these small events, but in this case, in this particular case, it managed to pick up such a small event. It's very useful for these smaller and medium-sized events because in those cases, water doesn't appear on the surface. This can go undetected for days or weeks or even longer, losing a lot of water. One of the other things that the system can detect, these are all basically real-life examples from real-life data. It can detect a sensor failure. In this particular case, there was a drift in flow sensor. You know, in these old-fashioned sensors, you have moving parts, and if a bit of dirt or something gets into the sensor, it starts drifting or for some other reason. It basically gives you wrong readings. But look at it here. You know, this is the scale. This is a number of days. You know, this is 2 days from here to here. So basically, the system picks up a fault in a sensor several days before it's visible, or at least a day before it is visible to a control room operator. Assuming control room operator would have time actually to look at all the sensors in the system. Sometimes you have thousands of these in the system. And a final example is the example of detection equipment failure. In this case, we have a PRV, pressure reducing valve. So one of these DMAs is PRV controlled. It's a fixed setting PRV. So the pressure under normal conditions is near constant downstream of the PRV. This is the flow meter at the same point. This PRV is located at the upstream point of the DMA. It's controlling pressure in the whole DMA. And at some point, pressure starts fluctuating even though there are no anomalies in flow signal. And that's because the sensor became faulty. And the faulty sensor leads to a first pipe burst due to material fatigue. The company went out, fixed these bursts, and a few days later there was a second burst. And then they realized... Sorry, there is someone background noise. Can you please mute?
Mute yourself.
Please mute yourself, yeah, thank you. So there was a second burst, and then the company went out and investigated because this was not used.
Ese no fue el director, no, ese no es.
El director de
Del Montes. Pensé que del UNITA, pero el del UNITA era, ¿cómo se llamaba?
Maybe the organizers.
Bansil.
Okay, so they went out, investigated, detected a second burst, and then investigated the whole thing and realized the valve was faulty. Now, this particular system was not in use then, but if it was in use, this is where it would have raised an alarm. As soon as the pressures started oscillating in an unusual way in the pressure signal, and this is almost 24 hours before the first burst. So if the system was in place, you could argue that this faulty equipment would have been detected on time and possibly replaced or fixed before either of these two bursts happened. So you could basically be proactive with this sort of systems as well. So what is the end result of using these elements of this system? Not everything were built into a commercial solution. It was tested and validated. We tested this first on historical analysis by feeding the historical data through the AI system. Then we used engineered tests where we went into the actual water system and we opened hydrants to simulate bursts, collected data, and then did blind tests. And ultimately, the system was let to run for 6 months. And then to test real leaks and so on. It was validated. It enables fast and reliable detection. At the time, I was told that it typically detects bursts within 15 to 30 minutes, so 1 to 2 time steps since the bursts occur. It was a reliable detection. We worked out that the number of percentage of false alarm was not more than 10% at the time. This system has been used in one of the companies in the UK since 2015. I don't know if they still use it or not, but it was used then. And at that time, it was processing data from 7,000 plus sensors. And this is the main motivation why we kind of stayed away from the EPANET and similar hydraulic models. When you have this large number of sensors and only 15 minutes to process the data, using hydraulic models is not really an option on nowadays computers unless you use something really powerful. The other reason is that these models are anyway usually not that well calibrated. Even when they are in companies, sometimes they just don't exist. And even when they are calibrated and exist, they're not that well maintained. It's very expensive to have a repository of these models constantly updated in a company. This resulted in major operational cost savings and other benefits. The water, for example, the water leak, the leakage reduction was at the level of that it was sufficient to enable the company to ultimately improve its supply-demand balance, supply-demand ratio, to the point that they were rewarded by the regulator financially for that. And of course, yes, we applied for and received a number of awards for this over the time. So some take-home messages. AI has potential to address a wide range of challenges in the water sector. I've just given you one small example. I'm sure you're aware of many others. AI-based solutions work, as you can see from this example, and it can lead to substantial savings and improved service. However, if you want to make AI really effective, it needs to be combined with sound engineering knowledge, like I've shown you in this example, with that evidence collection, which was very much based on engineering principles. You can throw data at the AI alone, as it can be done, in the IT industry, but in order for that approach, brute force approach to work, you would need to have really a lot of data and a lot of good quality data, which we normally don't have in the water industry still. Even if we had it, why not use the engineering knowledge and make the job easier for the AI, combine it with engineering knowledge, if that works. And one final bit of warning, I'm seeing now, I've been involved in developing AI type methods for a long time, and it's become really fashionable now. And I see a lot of researchers, a lot of people trying to do something with AI, even when it doesn't really make sense. AI is not necessarily the answer to everything, okay, in the water sector. Use the AI when it makes sense to use AI. There are perfectly fine solutions without AI as well that have been developed over the works over the years and so on. That's it. Thank you. And I don't know if I'll be taking some questions now or later on, but I can stay only for about 1 hour in this meeting.
Very much, Zoran. Truly fascinating. I think we agree that the questions will be held till the end. So we'll now turn to Dr. Stefano Galelli.
Just give me 1 second to reorganize all the windows here in my computer. So you should be able to see my screen now, right?
Yeah.
Yeah, we can see just, yeah.
All right, perfect. Okay. All right. So first of all, thanks for the invitation to speak today. I'll be talking about another application of AI, if you will, and particularly I'll be talking about the problem of detecting and localizing cyber attacks in water distribution systems. Now, before doing that, let me acknowledge a few important people. Andres Murillo, Ricardo Termina, and Neil Stippenauer and I have been working together in Singapore for a few years. We all now are in different places, and along our path, we work with Avi, who I'm seeing here, Elad, Demetrios. At some point, we worked together for a data competition. So what I'm going to show you this morning is the combination of the results of several years' work with a number of important people. Now, first of all, why are we interested in cybersecurity of water distribution systems? And if perhaps you haven't heard about this problem, why this could be a relevant problem? Now, to answer the question, let me take a very short step back and go perhaps more in the direction of what Zoran was talking about, which is the modernization or digital water or water 4.0 paradigm, which is delivering a number of important and desirable features. For example, it can help us make system more reliable if we can, for example, detect a pipe burst faster and therefore fix the problem quickly. It can make the system more autonomous because we're able to monitor and operate these systems in a more effective way, and therefore it can make the systems more efficient. However, as we digitalize the urban water sector and the water sector more broadly, we may have some unintended consequences, one of which are vulnerabilities to cyber attack. So why does this happen? So what you see here on the left-hand side is a representation of what we call the convergence of OT technology, operation technology, and IT technology. So what you have here, essentially on the left-hand side, at the bottom, are field data elements, for example, pumps, pipes, sensors, etc., which in the Water 4.0 paradigm are essentially controlled by distributed microcomputers like PLCs. What you have on the top is typically the human-machine interface, for example, in the form of a tablet, of a desktop computer, or even a mobile phone that allows us to monitor and operate systems in real time. And if you look at the water distribution systems in particular, what you're going to have is something that could be roughly represented in this diagram here in the center. Again, on the top, you have the information technology. On the bottom, you have the operation technology, and the convergence of IT and OT can create a few issues. For example, IT and OT networks have different priorities. OT has to be available all the time for reliability, of course, to provide service, but it's not necessarily designed to support cybersecurity, especially those that were designed a few years or a decade ago or 2 decades ago. Whereas IT has a completely different purpose. And the problem is that if these systems are not designed and integrated properly, what we can experience is essentially the increase of vulnerabilities, which could be exploited. For example, a cyber attack can be perpetrated starting from the human-machine interface, for example, from a desktop computer which has access to internet. This is actually often the case, and then can trickle down essentially to the physical system. So these are the results. This is an illustration from a paper we published just a few years ago. It was a review of cyber attacks in the water sectors for the past 10, 15 years roughly. And one of the interesting things we found is that attacks were increasing in number and were also increasing in complexity. And in our review, we stopped in 2020 with attacks. So yesterday, as I was preparing for this talk, I just went back and looked at more recent events. And a very recent event happened in December this year in Pennsylvania. And in fact, it turns out that other US water utilities have been hit by attacks. So these are relevant and particularly, I believe, interesting problems. So what I do in my research is to deal with some, of course, not all, of the technical challenges that are related to cyber attacks for areas in particular of interest, collecting and generating data. We don't have so many data that describe cyber attacks. So if we don't have data, it's hard to learn how to make things better. Characterizing the response to potential attacks, identifying and localizing cyber attacks, which is what I'm going to talk about today, and designing reactive measures. By reactive measures, I essentially mean any decision of management nature or planning nature that we can take in order to make the systems more resilient, either before an attack or during an attack. But for today, and in particular for the relation with AI, with these teams, let's talk about identifying and localizing. So how can we do that? Well, this can be framed as a detection problem. In a way, I wouldn't say similar, but you can see some relation between what I'm showing now and what Zoran just showed you with the problem of detecting, for example, pipe bursts. So we can frame, for example, this in the form of a classification problem, which therefore you can tackle with AI. And in the problem, we want to determine whether the system is in normal operating conditions or not. And in this case, AI, and in particular machine learning, can be rather useful, especially with the new architectures that come from deep learning. Again, that Zoran has already mentioned, they can be trained or tested pretty much on any water distribution system as long as good data are available. And this can help us implement these detectors in real time. One may argue that it can take time to train a very large, complex deep neural network. And this is true, particularly if one doesn't have access to GPUs or, let's say, state-of-the-art or advanced computing systems. But once they're trained, they're pretty fast to run in real time. So if you're receiving data every 5 or 15 minutes, if you're running your detection algorithm in real time, then machine learning, I believe, can really help. So in our particular case, the type of detection system we used or played with is an autoencoder. For those of you that are not familiar with it, The idea essentially of an autoencoder, what is it? It's a big, deep neural network. The fundamental characteristic is that the number of input layers is equal to the number of output layers. Sorry, input nodes and output nodes. So what this neural network is learning is a representation of the input variable. How does it do that? There are two phases. There's a compression phase where essentially we are extracting the key features that characterize in the system dynamics, and then there is a decoding phase. If this sounds like something you don't really understand, sorry, be patient with that. If you're more familiar, for example, with, let's say, principal component analysis, you can see this as a principal component analysis just in a nonlinear fashion, where you first compress your data and then you invert your principal component analysis to decompress the components that have been trained. Now, if we're essentially learning an input-output function, how does this help us with detecting cyber attacks, or if you will, any type of anomalies more broadly? So here's the idea. We can train and validate in normal operating conditions and look at, for example, the average reconstruction error. If our autoencoder has been trained and validated properly, then when we run it in real time, it shouldn't create large anomalies in the reconstruction error. And if we do find large reconstruction anomalies, then there might be a problem, for example, caused by a pipe burst, or for example, caused by a cyber attack. So to test it with this idea, we work with the data set that is called the Battle of the Attack Detection Algorithms. This is a data set that was created a few years ago for one of the data competitions. There's some background noise. This is a data set that was created a few years ago for one of the battles of the WDSA community. Very briefly, what we did was to create two main data sets, one without attacks, one with attacks. This was done for the benchmark network of C-Town, and we had multiple variables. You can see here on the top right, all characterizing physical processes. So water level, water flow, water pressure, and the status of a number of pumps and valves. And this is just a representation of the system. So how does the detection system work? So here you can have some results. I would ask you to focus just on the central one, at least just for the moment. This is on the test data set. There were 7 attacks. You can see them in black. So this is showing whether essentially the system is under attack or in normal operating conditions. And in gray, you have our detection. So is this good result or bad result? I think there can be different perspectives. If you are talking to somebody that is primarily focused in machine learning development, they will probably tell you the results are reasonably good. The precision, which is the ability to prevent false alarms, is close to 1, which is the best ideal result. Recall, which is the ability to detect attack, is not bad either. But in Singapore, for example, we have a test case, a physical test case, where we were running also experiments. We were working with different companies at the time to test our solutions. And when you start seeing these false alarms, here, some of the company's managers or engineers will probably start to complain and tell you that false alarms are a big problem, and there's probably still a little bit of research that needs to be done. So I think conclusions of what is good or bad, especially in the field of AI, I think should be drawn very carefully. It's very easy to get excited by a very low mean square error or a high R-square or precision and so on. But I think once we start facing the reality and talking to operators and engineers deploying systems, then I think engineering considerations become, as Zoran was mentioning, very important as well. The difference between the central plot and the one that's on the top and the bottom is just a slightly different parameterization, which is showing an important thing, which is the tension that you can have between false alarms and false positives, as you essentially calibrate in slightly different ways your systems. For example, from central plot to the bottom plot, you can see that the precision decreases slightly, but we have higher recall. Again, there's a tension when you look at detectors in terms of how they can be sensitive essentially to different two different problems. Now, can we localize? And why localizing is so important? It's very important because if we want to take reactive measures, so deciding how to intervene, then we need to know where the attack is happening. We cannot only know that an attack is happening. So we can look at the reconstruction error that autoencoders have on the entire system, but we can also look at the reconstruction error that autoencoders have for each different variable we have been working with. So here on the bottom right, what I did was simply zooming into one specific area of the network that we know for the attack we generated was affected by the attack. And we can see in particular that for one of the sensors, we have a pretty high reconstruction error, which is essentially an indication that that sensor or that specific area, DMA in the network, was affected by the attack. So what are the disadvantages of challenges, I think, that can be easily seen? One, there's certainly a tension between the ability to detect attacks and prevent false alarms. And this in real world application is certainly a challenge. I've shown you briefly something on attack localization, but to be honest, I think we're pretty much struggling there. At the moment, we need to manually inspect each different output from the neural network and trying to understand what is happening or not. And data concealment is also a problem. For the record, data concealment is essentially a type of cyber attacks in which the attacker is also concealing the data we receive, and that makes detection and localization particularly challenging. So one of the questions we asked, and what I'm going to show you now is very recent, largely also unpublished research, is what is more data were actually available? So what kind of data I'm talking about? We do have, and I would ask you to focus just on the bottom for a second. We do have a lot of process data nowadays. We can generate them with models. We have all sorts of sensors, so we can measure level, pressure, etc. throughout the network. But what we're dealing with, and now I think we can focus on the top, is the fact that these are cyber physical systems. Cyber physical systems are characterized by a very large number of sensors, microcomputers like PLCs, etc. And as all these elements talk to each other, they do generate a lot of traffic, or to be more precise, network traffic. And in reality, they do generate gigabytes for large systems of data per day. And we never really look into this data. And these data typically come in a horrible form, which you can see visualized here on the top. And for example, this is the type of message being exchanged. This is who sent the message with a different IP. This is telling us who received the message. So the question is, what if we were actually able to look into this network traffic? Can we make sense of it? Can it help us? So what we did to answer this question was the fairly complicated, to be honest, but now it's working, effort of augmenting EPANet capabilities with a very detailed representation of cyber component. So to simulate the physical system, we use EPANets with two different types of wrappers, either EPANet, or Winter. And for the cyber layers, we use a combination of mini CPS and Mininets, which are essentially software that allows to simulate the behavior of PLCs, sensors, and all the computing system that you have in any cyber physical system, not necessarily only water distribution. So going back to C-Town, same setup as before, but now we have a very detailed representation of what is happening in each substations, which are the routers that are connected to each sensors, pumps, and PLCs, how they talk to the SCADA facility, and so on. So we are essentially able to generate now in real time two types of data sets, physical layer and digital layer. So can this help us detect attack better? So what I'm showing you here is, again, an autoencoder that has been trained just with the process data only. What you see on the top is one single attack in red, real state. What you see in gray are the predictions. All the different plots are essentially the different control loops that you have within the water distribution system. So a result, I would say, similar to what I've shown you before. We can detect attacks, and depending on parameterizations or depending on which specific areas, we may have to struggle a little bit with false positives, for example. Now, how about traffic network? As I said earlier, mentioned earlier, traffic network is ugly when you look at it. But if you extract variables, and this is what you see here on the left-hand side, there's a lot of information you can actually try to use. For example, the IP address. For example, if a sensor is receiving a message or sending a message to an IP address that has never been seen before, there might be something wrong happening. Or the type of protocol that is being used, the length of the packets that are being used, or how long an information takes to travel from one PLC to SCADA. This is all information that can be relevant. For example, if a cyber attack is penetrating a IT network and is poisoning the network, this happens often in cyber attacks, then the type of packets being sent, the IP address, the MAC address, or other information might have been compromised. So we should be able to see that signature in the data. And we kind of see it here. So now we're using an autoencoder that is working only with traffic network with these different types of features. We're looking at different PLCs. You can see that either a SCADA or particularly in PLC2, there might be something wrong happening. And now we put the two things together. Of course, that's the idea. And we look at the different control loops. We can see now pretty clearly that there is something wrong in the first control loop happening. So bottom line is, this is unpublished, and there's probably some lower hanging fruit, I believe, that could be grasped if we were able to work properly with all the network data, all the network traffic that cyber physical systems generate nowadays. So some reflections to conclude. AI is a great toolbox, as Zoran mentioned earlier, for different type of applications in the water distribution systems, and for sure for detecting and localizing cyber attacks as well. There's, I believe, still a tension, at least in the detection type of problem, between the ability of detecting problems, localizing problems, and preventing false alarms. And I believe this is still a problem when we try to deploy these systems in the real world. And I think, and this was my main message from the second part of my talk, that we need to go beyond the physical process data and try to work with also other data that cyber physical systems generate in water distribution, stormwater drainage, and so on. So for example, we don't really know the extent to which network traffic is useful, and if we extract features from it, which are the most useful. We don't really know how to combine them with process data. And this is, I think, a challenging problem, because process data, we normally work with a resolution of 5-15 minutes or so. Network traffic works in milliseconds. So we need to understand how to combine data that come from different data streams, but that have completely different dynamics as well. And of course, the overarching question is the extent to which this can be used to detect anomalies or other types of problems. Other applications of AI to cybersecurity in general, enforcement learning, could be particularly useful for real-time control, for data generation. So I think there's quite a lot there that can be done with AI. But to conclude, I would also like to reinforce Zoran's message. I largely totally agree with the fact that AI is a great tool for tackling a lot of problems, but it should be used with a grain of salt. Knowledge, physical knowledge about engineering knowledge about systems is always to be complemented when available with AI. And still, there are also problems that don't necessarily need AI for being addressed properly. For the data I've shown, Batadal, you probably heard of it. It's a slightly older data set now, but roughly a year ago, we released the Batadal 2.0. Perhaps some of you will be interested, where we essentially started to augment the process data with network data. And I think if everything goes as planned, in a few months, we will release a final version that includes all network data. And DALSIM is the new simulation tool we created to augment APANET with these capabilities. So with this, thank you for your time, and I'll be happy to take questions later.
Yeah, thank you, Stefano. Before we continue, we can pause here for a quick round of questions for both speakers, if anybody has any. Okay. So if there aren't any questions, we can go to Demetrios now, Dr. Demetrios Eliades.
Okay. You can see my screen, right? Tomer, everything else okay? Yes, you can see everything, right? Can I start?
I can see anything.
You cannot?
I can't.
Sorry. Okay. A moment. There is a question until I manage to connect. So if somebody wants to answer, maybe there is a question on the chat until I manage to connect the.
Stefano, do you want to answer, or shall I say something?
I can start, but you probably know more than me, Zoran, on that. So I'll let you finish. Let's do it this way.
Okay.
So I think there are a lot of ideas and opportunities. For example, one that would come to my mind is state estimation. So if you're running a, let me go back to the question, now it disappeared. Okay. If you're running a process-based or physics-based model, especially in real time, it's particularly useful in the case to keep essentially the model anchored to the state of the system, to the actual state of the system, where you would normally use some state estimation techniques, like, for example, a Kalman filter, which could, however, be improved by AI techniques. So one application that comes to my mind is using AI for state estimation, and then using that information to essentially feedback to the process-based model.
Indeed, I fully agree with you. And just to add to that example, there are cases where the physically based models either don't exist at all, or exist but are not really, that well developed yet. For example, I'm working at the moment on a PhD project which is trying to reduce nitrogen emissions at wastewater treatment plants. And the first step is to predict well those nitrogen emissions. And it turns out that all the process-based models that we have at the moment just can't do the job. So we are hybridizing them with AI, or they're developing AI equivalent of these models just to be able to do that prediction reasonably well. There is another question, but I'm not sure if we have time. Shall we, Tomer, shall we let Dimitris do his presentation? Or?
I think we... Right?
Tomer?
Yeah. I think we can go on to Demetrios' presentation, and then we'll refer to the question at the end.
Okay, you can see my PowerPoint now, right?
Yes.
Not my Star Trek background. Okay. So hi everybody, and thank you for the invitation. I'm really excited to be here and make this presentation. Just on the time. So it's a bit different, the type of presentation that I prepared, but I think it will resonate a lot with what Zoran and Stefano actually described. But I took a more personal point of view because actually AI is a core area of mine. So I felt that I want to say a few things to the students, and postgraduate researchers attending this presentation. So I have a background. First, let me say that I have a background in electrical computer engineering, and my postgraduate degrees in artificial intelligence and electrical engineering. And I went through more or less all the aspects, or most of the aspects of AI. I have been also involved in the IEEE Computational Intelligence Society for many years, and this will kind of drive what I'm going to say later on. So just keep this background in mind. Let me just say that I think it's important for me to communicate about how we started with AI, and I mean, like many people here, like the older people, maybe our first interaction with AI was Conway's Game of Life, where we realized the potential of artificial life, and And there, at that point, when I was a student, I was finishing my diploma, I got the sense that I want to be able to design smart software and hardware which are able to operate autonomously. So, you know, that was the inspiration. And during the next few years, I started going into a bit depth, into more depth. And I'm saying this because I want to emphasize the need to study AI. And AI is not just what you hear in the news. It's not just what you read in the latest paper from OpenAI. There has been a very deep, there's a very deep background, scientific background for this study, from game theory, from evolution of cooperation with Axelrod, artificial societies, multi-agent systems, genetic algorithms, which is actually one of the most favorite, I believe, technologies developed that were fully embraced by the civil engineers, especially because David Goldberg, his background was in civil engineering, and I think this played a role. You know, his examples in the book are with pipes, so at least for me that made a lot of sense. But this is more about how to evolve intelligent agents, and this was the early 2000s, let's say, end of 1995 to 2000s. Then afterwards, it was this data-driven approach, creating models of the world through data. And here is not just machine learning. We're talking about learning algorithms and information theory that are connected. So typically now we go straight to the peak of the iceberg. We have the deep learning methods, but the traditional standard methods for AI are still very relevant, and we need to be aware. We should know what to use when. So wrapping up, you know, all of these books are actually my favorites. But wrapping up everything, I would cluster AI in the logic-based approaches like Prolog there, statistical approaches like the book of Hastie, and also there is an area in control systems and optimization which actually very much related, and this is actually around the scope of computational intelligence. So in my title, I wrote about artificial intelligence, computational intelligence, and I kind of split it into three, in my mind, in three clusters. So we have developing things that we create agents that act and reason like humans. We develop algorithms for learning models from data, and also develop algorithms for optimization control. So knowledge models, and here we have ontologies, reasoning engines, which like first order logic, even I would argue kind of some aspects of large language models. These are agents that act and reason like humans. And knowledge models are essentially representations of the world in a Platonic sense, and the reasoning engine in something in Aristotelian sense, making sense with specific predicate of the world with reasoning and predicates. Of course, neural networks and other type of approaches like tree-based methods, supervised methods, etc. They all need data, so that's why they're there. But also there is another part which is not so. Of course, evolutionary computation is very popular here, I believe, but also approximation theory, online parameter estimation, even reinforcement learning. These are things that kind of relate with optimization and control, and it's very easy to lose, you know, to miss, and you know, sometimes you may want to use control theory, but you're using reinforcement learning, even though you could easily solve the problem by using you know, the classical theory. So it's important to understand the theory, understand when it's good to use that. So I'm taking now a step back, and I'm showing this figure now. I'm a system engineer. So the water systems, they operate in a very complicated way, but they have sensors, they have actuators, and for their operation, usually we have controllers, models for state estimation and machine learning. We have event detection, or already Stefano mentioned a lot of things, and also Zoran, identification, isolation, explanation of the faults, and fault accommodation. So everywhere here, we can have machine learning AI methods. Zoran mentioned before about the 5 stages of the 5 layers of smart water systems. And in fact, most of the AI happens at the top, but I would also argue that in the future, I envision that a lot of AI will go to the edge. So this is how I will close my presentation. So stay tuned. I'm going to show different examples from our research, and I'm going to explain if we have applied it and how we applied it and what was the result. But let me just give the high level vision, which is my personal vision. It is to use AI to use AI as a control engineer. So essentially, to design. So when we're designing control systems, usually we have expert people that need to design, where to install sensors and how these sensors are connected and how to design the controls. And the idea would be an AI system would focus on the autonomous configuration of this system. It should have a model representation of the system, of the water network, of the PLCs, of the type of sensors it's using, and be able to ask queries, semantic queries, to get complicated answers. So if you have an expert in a water utility and asking questions, how to set up this system, that person knows how to respond. How do we model this to a real into an automated system? And when there is a cyber attack or when there is a failure, the system should be able to reconfigure. So this is part of the work that I'm trying to promote. At the moment, still, this is very it's not there yet because it's based on AI, but still it's missing a lot of things. However, what we can do here is that we can integrate existing machine learning models into the knowledge base and use those as needed depending on the case. So for instance, if we are losing a sensor somewhere, we can replace it with a virtual sensor, essentially machine learning estimation. So that was my first pillar that I'm trying to develop. But we also a lot of times in our domain we're using AI for optimization, decision support. So most of the things I'm going to say now, everybody knows them, but I've just seen it for completeness. There has been a tremendous amount of work in this field in the area of evolution computation for single, multi, and many objective, specifically for the optimal placement and selection problems for pressure, quality sensor, and valves. Here we have linear and nonlinear objectives. Sometimes they cannot be computed mathematically and they need simulation. So it's a challenging problem, it's an epic hard problem. And of course, I believe that a lot of people know how to solve these problems, especially for the people who are not aware of it, though. Genetic algorithms and evolutionary computation is part of AI, the broader AI sense. And the idea, of course, is to be able to find a set of Pareto solutions. It's actually quite trivial to do this nowadays. The most difficult part would be actually to formulate the problem in a suitable way. So usually you have a complicated optimization function and you're trying to solve it. So, the questions are how to discretize the variables and how to be sure that you are getting a good spread of solutions. You don't need to use evolutionary algorithms. You can also use tree-based methods. Search trees are actually quite well established in AI, and you could modify these algorithms to serve your needs. So my point is that usually we take algorithms for granted and we just apply them from like scikit-learn or something like this. But we can design our own algorithms, and sometimes these algorithms can create an advancement in the field that was not expected. So something that I did is that we did a game for sensor placement. So essentially, we solved the problem of sensor placement using we left the evolution algorithm to run for 2 minutes, and then we created the same game for this game for people to try, like children or experts or whoever, students. And it's online, and people are running and trying to find the optimal sensor placement for this network. And we actually give the Pareto front. And up to now, almost more than 200 people have played this game, and nobody has ever reached the optimal solution. So this is for me, it's very indicative that even though people are able to reach are approaching the Pareto front, nobody has ever achieved any of the Pareto optimal solutions that the computer was able to find in 2 minutes. So for me, that's already enough explanation to say that AI tools work, and how this compares with the expertise. But by the way, the people when they're trying this are following an iterative approach. So actually, the approach is closer to this search tree. So this is closer to how humans try to solve problems. And of course, there are other type of problems which are again solved in a similar way. This is for deciding which pipes to close. If you have dynamic valves in the system. But again, these are solved using evolutionary algorithms. Another type of problems is manual sampling. And here, you can use decision trees. And actually, this is another modification that you can do to the algorithm. So where to conduct manual sampling in order to be able to detect and infer the existence of contamination events. And actually, this is something that we tried. Another expansion of this is to find the source of the contamination. So where to sample, and depending on my sample readings, to be able to identify if where the contaminant is. So there, for instance, I do a sampling. I immediately split my area of potential scenarios into two. So if it's red, it means that it's on the left side. And then this is left, and then it continuously splits the set of solutions until I'm able to isolate the actual location of the event. And actually, we tried this in Amsterdam as part of the Pathos project with human experts and with KWR, and the results was that the system was able to provide fast solutions faster and in a more efficient way than the human experts. And this is because, of course, the human expert has a lot of experience, but they don't know all the dynamics that are hidden in the system. So something that is not typically used in this community is the use of real-time online learning. Usually people are using batch learning, and that's okay, but sometimes want to learn things as we go, as things progress. And here, it's where we need the mathematics and the mathematical understanding of what neural networks, but also approximation functions in general are. So we have polynomials, radial basis functions, Fourier series. So these are pretty standard. I know that they don't sound very exciting, but they are approximation functions, and neural networks are universal approximators of, in a similar sense as polynomials. So we can design, and here I'm just showing an example that we did for the Computational Intelligence Society. We can design our own laws about to update these parameters. And here what you see actually is a combination of the physical dynamics. So these parameters, these variables above, these are physical dynamics. What we don't know is for instance, here are the reaction coefficients of chlorine. So we don't know how chlorine reacts. This is what we don't know. But what we can do is create an estimator to learn those dynamics. So what we are doing here, we are combining the physical model. So that was a question before. We have the physics-based modeling, and we have a part that we don't know, and we are trying to learn that part. We don't need to learn everything. That's it's not the optimal way of doing that. So again, as I mentioned before by Zoran, state estimation, it's also another thing that is being used. And again, it's the same concept of updating all the time, updating the system, the parameters to find the optimal, to find the demands and eventually the flows representing the system. Now, going now to the edge, we have now edge devices. So for instance, we can imagine, so this problem that actually has been solved by various other people here in the panel, but we're talking about the demand disaggregation and the domestic water use disaggregation. So the idea would be here to design machine learning systems that are able to detect whether when there is one sensor in the house, whether the tap water or the faucet or the washing machine was used. So what you do, we have developed this platform that generates data, and we have evaluated different types of machine learning approaches, SVMs, random forest, XGBoost, of course, MLPs, multi-layer perceptrons, and also evaluate this with model-based methods. So these are the more traditional methods, which are based on model, time series analysis, etc. Now, in the end, we selected the MLPs, and we wanted to move this to the edge. So the problem is that you cannot always have cloud-based solutions that are running machine learning systems all the time. You cannot send all the data to the cloud all the time. That's not really practical. What you can do is that you can push the neural networks to the edge, and of course, like OpenAI now is doing, trying to reduce the size of the sorry, not the OpenAI, Llama and other LLMs are trying to reduce their size so they can fit on small embedded devices. The same thing we did here. We are using TinyML. Is a platform that is based on TensorFlow that allows you to reduce the size of the model that you have trained, so that it can fit on a small embedded device. And this is an embedded device that we designed, and was able to actually detect events more or less at the same level as the large network. In closing, some new opportunities in AI. I mentioned before about knowledge. I started with knowledge graphs and ontologies, and I'm closing with this. So it's easy to create based on knowledge and experience, and even now with LLMs, we can create knowledge graphs, which actually consolidate knowledge and create all of these relationships between the different elements. So, for instance, when you have an earthquake, there can be a pipe break, and when there is a pipe break, there can be infiltration of a pathogen, and we have 10 different pathogens, and this pathogen can cause this vomiting, let's say. So, if I observe vomiting from my customers, what are the possible causes? So I can ask this by using the classical reasoning, SparkQL, ontology. These are the more classical ways. But of course, we can combine this now with custom-made LLMs, and they can give us this graph analysis. They can give us an explanation of what we see here. So what you see here is not ChatGPT. I mean, it is ChatGPT, but it has been loaded with this graph network to illustrate. And as I ask a question specifically for this data set, for this database, and it's giving me an answer based on this data set. It's not creating any new knowledge. It's not doing anything else. So it's easy. Well, at least it seems that the path to explainability is becoming more easy to access. I'm closing with the benchmarks. It was mentioned a lot by Stefano, and I fully adopt and agree. It's very critical for people doing this research to have realistic data sets for hydraulics and quality, and security, etc. Our team has developed a lot of benchmarks. We have the LinkedIn, which is actually specifically designed for machine learning experts. We have the battle competition as well for the battle of the leakage detection isolation. We have the water safe benchmark, which is actually a physical benchmark in a similar way as it's in iTrust, I believe. And also Dalsim, it's a great tool, and I also fully support the use of it. And of course, the use of simulation tools and wrappers, like we have recently released the APNet Python toolkit and the MATLAB toolkit. This can enable us to generate realistic data. So what I think we need to do is develop more data sets. I think this will drive interest to the field of machine learning people, but also it will help us as a community to grow more mature in the use of machine learning tools. And yes. So in summary, it's very important to try to get, if you're a student, it's important to have a strong mathematical foundations. You have to get them right. You have to understand the broader AI in a broader concept, context. You have to understand when it's better to use analytical instead of, or even together with machine learning methods. Not all problems need machine learning, and machine learning is not AI. AI is something broader, and we need to understand that. Something that was maybe not mentioned, but is critical for me, is the handling of uncertainty and the consideration of bounds. It is possible to produce bounds with machine learning methods. It's a bit more complicated, but I think it's more important. It's important, or other maybe probabilistic approaches as well. But bounds are important because sometimes just solving a regression problem with just a value is not sufficient. It's not sufficient for our work. It's critical to open your research data if possible, sharing your research code if possible, and organize as many battles and competitions as possible. And a bit of shameless here advertisement. We are hiring, so people who would like to work on these things. We have a great place to work and to live. So that's it from my side, and thank you for your time, and I'm sorry for the delays.
Thank you very much, Demetrios. We can now open the floor for questions. There's one question in the chat now, which is, can you comment on benefits of physics-informed neural networks?
maybe I can continue since I didn't answer any of it.
Yeah, go ahead.
Yeah, okay. So I think physics inform neural networks, or in general methods that try to learn the physical aspects using neural networks are very important, and we should investigate them more, especially for water quality modeling. I think there is a good potential for fit. Of course, there is the context of there are also other techniques like graph neural networks, which are also we have seen that they are quite also relevant and useful. Don't forget that water distribution systems are primarily it's a physics-based system. It's at its core, especially the hydraulics and especially the water quality. So I believe that there is a lot of room for improvement there, and hopefully this will alleviate some of the challenges that we are faced when using EPNet, for instance, for modeling.
Maybe I can add to that before I leave, because I really have to go now. I think this is a little bit different from AI complementing the physics-based modeling, so which Stefano and I discussed a little bit earlier. The main benefit of physics-informed neural networks is to help basically train these networks in a way that it uses knowledge domain, that uses the knowledge of physics, which should help them, train them either faster or to predict more accurately and so on. And this can be done in all sorts of different ways. It could be a simple constraint that you put on a prediction variable that you know from the physics what is the possible range and so on. But it could be that you're developing a meta model of EPNet and you have a well-calibrated model which you want to emulate, and then you just run that model with all the physics behind it to create the training data set. And if you prepare the training data set that it's representative in a way, you can actually shorten the time required to train the neural network, or you can make it more accurate and so on. So effectively, I think the main benefit of physics-informed neural networks is to really help you do the machine learning more effectively, either faster or more accurately, or both. But this can be done in many different ways, of course. I will have to really leave now. I have to pick up my wife from the train station. I already stayed a bit longer. Thank you once again for the invitation, and I'll have a look at the recording. If anyone has any questions for me, feel free to share with Tomer or Magna. I think they have my email address. So. Thank you.
Thank you very much.
Bye-bye.
Are there any other questions?
I think there is another one in the chat.
Yes, I'm reading it. It's a difficult question. So let me read it, and long. I'm still reading it.
In the meantime, I'm going to quickly say that yes, in answer to Brian's question, we'll be sharing the recording in the next video.
So I can start to answer this question, but perhaps different people may have a different interpretation of this question. I'm not sure exactly what is meant in this specific case with democratization of newer ML and AI as against pushing the boundaries of the application of them. Yeah, so certainly there's a challenge in the AI as a broad domain and ML as a subdomain that is related to the fact that there are many advances being pushed almost on a daily basis. So I think it's very difficult to stay on the top of everything that is happening. So being on the top of that development and translating that or taking some of that research and apply it to engineering domains like water distribution system analysis is certainly a challenge. And I think that could create some issues of inequalities, for example, because not all the time we have the knowledge, we have the computing tools, for example, to be able to test everything that is there. So that's how I'm interpreting. I'm rereading the question essentially and trying to interpret what was meant in this case with democratization. So there can be, I see some issues there, and I don't think we have a silver bullet solution yet to that problem. On the other hand, what I would say are probably a couple of things. One is that even more, if you will, traditional tools in ML, like even a multi-layer perceptron, can do wonderful things. So we don't need all the time the most advanced architecture, the most advanced machine learning models. And with the fact that we will be moving from solutions where AI is at the top, as Demetrios was showing, to solutions where also ML can be distributed in engineering systems, including water distribution systems, then simpler models that are also very popular in industry, I think, will be able to do the job. So I don't think the only research question is how does the most sophisticated tools apply to my problem. I think it's a broader question of what, when, and how we can use a much broader spectrum of tools. The second part of my answer related to democratization is the fact that there are luckily a lot of online solutions that we can run. So if computing facilities, local computing facilities are a problem, we do have now opportunities to run things online.
If I can just say a few things as well, Stefano. So I have also some opinion, because I coming from a country that was we were not the state of the art, let's say, in the area of ICT, but however we did try, like almost 10 years ago, we set up a system, for instance, using machine learning to analyze every day the DMA inflows and the pressures and provide a risk assessment, let's say, using threat analysis and running some basic machine learning models, try to figure out what's happening with their system, and they were using it to prioritize. This was a job that for them it took like 2 weeks, maybe 3 weeks, to collect all the data, put on an Excel, and we did it using an automated system that is running since 2015-16, and we every day. So essentially, what we can achieve is that if we demonstrate the value, I think the important thing is to demonstrate the value. So if we demonstrate the value of this thing, the utilities, the operators will see it, and they will use it, and they will understand it. It doesn't matter if it's complicated or simple, as long as it gives them something that is along the lines that they expect. So Stefano mentioned, for instance, the issue of false positives, and maybe they just need something that is sometimes correct but never wrong. And maybe that's simple for us, for academia, but for them, maybe that's the thing that they want, and we have to start giving them that before going to the next level. So we cannot really change everything and replace everything with an automated system, even if we have the tools. However, I was going to say about it. So I was going to say something though, that especially for developing countries like Africa, where essentially there is such a decentralized water operation, the use of AI and the adoption of AI seems more relevant. And I would argue that there it might be beneficial to invest for these new, more exotic and more autonomous technologies that are able to support small communities, especially now in the fast development of Africa. And one way to do that, and I'm closing here, like for this section, is for part of the question. For instance, the issue of transfer learning. So it is possible to train neural networks. Let's say that we're training a neural network for pump failures, and you use Germany as a reference, you use Spain as a reference, you use your neural networks, you are training this, and then you can take these models that you have learned, and you can put them in a different context in a country where they don't have so many pumps, they don't have this ICT infrastructure maybe, and they're using all this knowledge that has been collected in a different location, and they don't need to train on their data. They can they can use it to monitor their pumps on a totally different setting. Of course, it's slowly, they need to adapt with their own settings, but this is actually something that's going to bring some democratization, I believe, in that sense, in some sense of fairness in the way we manage water systems today.
Yeah, thank you. There's another one in the chat. Maybe I'll just read it out loud. What are your views on applicability of AI for real-time modeling? And how would a standalone AI data-driven model perform in comparison to hybrid?
Demetrios, I'll start again and then pass it to you. Is that right? I think the answer is really, and perhaps it's a simplistic answer, but I think the answer is it depends on several different factors. First of all, I think it depends on what we mean with performance. And different researchers, different engineers, and in particular, different problems require us to define performance in different ways. So going back to something that I think Demetrios mentioned earlier, formulating our problems correctly and understanding the uncertainty around them is very important. And there will be instances in which we don't need AI at all, and setting up, for example, EPA-NET to characterize a given problem essentially does the job. There will be instances in which, for example, we don't have enough data, and in that case, to set up, for example, an hydraulic model, but we do have enough data, for example, to set up a simple or perhaps more complex AI model. And in that case, it will that technical solution will do the job. So I don't think that physics and process-based models compete with AI and vice versa. I see these more as complementary tools. Sometimes we can use one, AI, sometimes we can use the other one, or sometimes we can use them in combination. So I think with the growth of AI that we have, I don't think that process-based model would be ever pushed out because they characterize all the system and hydraulic knowledge that took us centuries, literally, to create. I think we have great tools that we can put together. So I don't think we should see performance as a competition between different solutions. I think we have to see them as complementary modeling or engineering strategies, to put it more broadly.
Stefano, I agree, but I want to say that because I'm coming also from a control engineering background, right? So in the control engineering domain, which is, I mean, it's comprised of mainly of people from electrical and chemical engineering background and mechanical engineering, sorry. There is a lot of research and there are a lot of people working on real-time modeling or real-time on adaptive, on how to learn online the dynamics, the unknown dynamics of a system, the interconnections, etc. A lot of people, and this is a very well studied problem, and there are a lot of mathematical theorems about, and there are a lot of theorems about it. So, you know, it's not just using a tool. I mean, of course, of course, in that domain, they go into the actual details. So when I said in my presentation that you can design your own update, update laws, it means that it's not you are computing mathematically the equivalent of gradient descent, let's say, and you can do this by using Lyapunov theory. So there is a set of theory that you can use to do that. So it is a bit complicated though, which is not maybe accessible for everybody. So what I'm just saying is that there is a balance between what you can do and what's and also the flexibility. So sometimes these analytical methods, they make some assumptions that are not realistic. They assume that you have data all the time. They assume that you have, so they make some other assumptions that maybe we are more free to handle them using machine learning. So I do believe that there is no silver. I agree there's no silver bullet. I think that it's depending on the case. However, it's very critical. I'm just emphasizing this all the time, but you know, not just because we know this tool, you know, it means that this is the best tool to solve the problem. Because, and I will share a personal story now, and which was one of my biggest mistakes in my life. So when I did reinforcement learning at the university, I felt that it was not really that important, because essentially what it was doing was replicating all the examples that they were giving us. They were examples that, like a first year control student is learning, like how to balance the inverse pendulum. And we knew how to solve this analytically, and then people were solving it using reinforcement learning. So I felt, maybe this is not such a powerful tool. And 5 years afterwards, or 10 years afterwards, like everything now is relates with deep reinforcement learning, etc. And I kind of missed that wagon. But because I thought that the analytics would be more powerful, but eventually in the long term, the analytical approaches couldn't solve the most difficult problems that were solved by machine learning.
Yeah, there's another question for Demetrios in the chat. Probably gonna be the last, because we have to finish in 2 minutes.
I just put a link on this. It's not competing. It's an evolution of the APNet MATLAB toolkit, and it has some more functionalities. But there is a link there in the chat, so people can check it out.
Does anybody else have any questions? Okay, so if not, I think we can all thank Dr. Stefano Galelli and Dr. Demetrios Eliades for joining us and presenting today. Thank you very much for being here, and thank you everybody for joining.
It was our pleasure.
Yeah, and as Magna said, as Magna mentioned, we're going to upload this recording online, and it's going to be available for everyone. So thank you.
All right. Thank you very much again. Bye-bye.
Have a great day. Bye.
Thank you, everyone.